Hello students, today we will discuss magnetic field, magnetic force, how this magnetic field and magnetic force is affecting on a moving charged particle. If this force and field is applied to the moving charged particle, some torque is produced. Using this torque, we will calculate magnetic dipole momentum as well as potential energy to this moving charge particle. So, before going to this, first we will see what is magnetic field and magnetic force, then we will come to the torque. Magnetic field, this magnetic field is produced for the moving charges. Suppose I am taking a particle, it is moving on the space, some field is produced. Whatever the field is producing is called as a magnetic field, and to this magnetic field, how much field is produced is called as a strength of the field. We are calculating magnetic field as well as the strength of the field. This strength of the field is represented with B. To this one, we are also writing units. First, we will see magnetic field. So, whenever there is a magnetic field, obviously some force is producing. Whatever the force is produced, that force is called as magnetic force, and this field is producing by the charged particles. Suppose I am taking a conducting wire, current carrying conducting wire. This current carrying conducting wire I am placing near the some magnet having north and south poles. At that time what happens? Some current is producing. How this current is produced? The current is produced due to the effect of the field. Whatever the field it is producing is called as a magnetic field, and the corresponding force is called as a magnetic force. So, here when we are discussing the term force, which type of force it is acting on the particle? Here we have two types of forces. One is normal, we will use the term called force, another force we will call as a rotational force. Here what is the difference between force and rotational force? In general, we know force equal to mass into acceleration. The same forces exist around a fixed point using some axis. Suppose I am taking x axis and y axis. So, along x and y axis, the force is producing from towards x to the y, then it is called as a rotational force. If some pressure in general I am to the one particle, if I am applying some force, that is called as general force. So, to this current carrying wire, when field is applied, we are getting rotational force. Here one more term we are using, the term is magnetic induction. Here the magnetic induction represented with B and the units is Tesla. What is this magnetic induction? The strength of the field at the specific point represents the magnetic induction. Before discussing our topics, we have few basic terms. What are the terms is useful in the next derivations means we will use the terms drift velocity, current density and rotational force. Suppose in the charged particle, suppose consider a conductor from left to right side. As we are passing, as current is passing, some velocity is produced. So, how much the speed the particles is passing, we will use the term as average velocity. So, the speed in which the particles is passing from first side to the last side is called as a drift speed or drift velocity. This drift velocity is represented with Vd. Next term we have current density. Suppose I am taking some area, in some area how much current we are passing. Suppose I am taking the length L, in that a small part I am taking dl. So, in the dl space how much current is passing per unit cross sectional area is represented with current density J. Next we have another term called rotational force. Just now we discussed general force as well as rotational force. In rotational force, some force is applied on the fixed point. So, from x axis to y axis how much angle it is changed is called as a rotational force. After rotational force, the main term is field. So, this field is producing due to the charged particles. This charged particles is whether stationary particles or moving charged particles, or this field is producing by the within the conductor or outside the conductor. Suppose if the field is producing inside the conductor, we will call it as a intrinsic. Suppose this field, the same field is producing outside, we will call it as a extrinsic field. So, field is produced by the moving charged particles, not by the stationary particles. Next we will see, suppose a charge, suppose I am concentrating on the space, some charge is placed near the place. So, what happens in the space, I am bringing one charged particle. At that time what happens, another charged particle is brought, some force is exerted there. Whatever the force produced by the charged particles, that force is called as a electric field, and the corresponding force as a electric field force. So, here I am discussing two terms, what is electric field, what is electric field force. In the space, bring one charged particle, its environment is changing. I brought another charged particle. If I brought another charged particle, the field is produced in that space. Whatever the field is produced in that space, I am calling that field as electric field, and between the field and the charged particle some force is produced. That force is called as electric field force. Here the force is of two terms. One force is produced due to the magnetic field, the force is produced due to the electric field. So, in the magnetic field I said force we are getting, the force we are getting due to what? Charged particle. So, when the force is produced due to the charged particle, we are measuring how much field is produced in that environment. The measuring of field in that environment is called as magnetic field induction, and the units we will take as Weber per meter square, or we can call it as a Tesla. And our topic now, we will see the topic action of the magnetic field on a moving charge. Suppose I am taking right hand thumb rule, Fleming's right hand thumb rule. In this right hand thumb rule, I am taking V as the velocity, B as the magnetic field, F as the force. Always remember that velocity and magnetic field. Here how velocity is producing in current conductor. When some field is applied, obviously it will take drift velocity. So, the velocity and magnetic field both are perpendicular to each other, then only here the force is maximum. So, we will see using right hand rule on which direction force is maximum. Here we have two figures. First figure is force is in upward direction, and velocity and B is toward adjacent with each other. So, this force is maximum when velocity and B are perpendicular with each other. So, here we are concentrating on the direction of the magnetic field. This direction of the magnetic field is depends upon the two factors. The first factor is velocity, second factor is on magnetic field, whether these two are perpendicular with each other or not. If perpendicular to each other means I am concentrating between the particle is 90 degrees. If suppose these two are not perpendicular with each other, then velocity as well as magnetic field both are in 0. At that time the total force we will take it as a 0. So, two condition, either F is 0 or F is 90 degrees. When F equal to 0, if velocity and magnetic field B both are either in parallel or in anti-parallel direction, then force equal to 0, or else velocity and magnetic field both are in perpendicular to each other, then only force is maximum, which is shown in the first figure as well as in the second figure. Next, using this we will write the expression force equal to charge. Here we will take Q as a charge, V is the velocity, B is the magnetic field. So, what is the formula we are using? Force equal to charge times of velocity into B. This velocity and magnetic field I am taking as a vector product. We have two terms, one is scalar product, another one is vector product. In scalar product we will use dot symbol, in vector product we will use product cross symbol, multiplication symbol. So, here velocity as well as magnetic field both we are taking as a vector field. Suppose if I am applying some angle between the velocity as well as magnetic field B, if we apply some angle, I am treating the term as a sin theta. So, what is our original formula? The original formula equal to F equal to Q times of velocity into magnetic field. Suppose some angle is applied, again that angle is either 0 degrees or 90 degrees. If V and B both are right angle to each other, at that time theta equal to 90 degrees. Suppose V and B both are not in right angle with each other, at that time theta equal to 0. That theta equal to 90 or theta equal to 0. Where we are applying? We are applying to the formula F equal to QVB sin theta. In that keep sin in place of theta 90 degrees. At that time what we will get? F equal to QVB. Suppose I am keeping theta equal to 0. At the time what happens? Force equal to 0. So, this is what we discussed, action of the magnetic field on a moving charge. So, how field is affecting on the charged particle, not a stationary particle, particle is moving. two types of forces. Again in the two types of forces, when the force is maximum, when the force is minimum, we discussed in this action of the magnetic field, that is represented here with the formulas. After writing two formulas, just I am substituting in place of theta 1 0 degrees or else 180 degrees. If we are substituting 0 or 180 degrees, at that time what is the force? Force is obviously 0. This 0 is applicable for velocity of the particle as well as magnetic field, is both are in either in parallel or anti-parallel, or else completely there is no charged particle. If completely no charged particle, then also F equal to 0. When both are right angle to each other, then only we will get force F equal to QVB. Suppose there is both electric field versus magnetic field, both the fields are there near the charged particle. If both the fields are there, electric field is represented with E, magnetic field is represented with B. At that time our formula will change. Actual, what is our formula for the magnetic field? F equal to Q times of V cross B. That is the formula for only magnetic field. Suppose in that I am including electric field. If electric field is included in the formula, then the formula will change. What is the formula we will write? F equal to force of electric field as well as force of magnetic field. Here the force of electric field is represented with Q times of E, whereas force of magnetic field is represented as Q times of V cross B. Both are combined together and the new equation is formed. What is the new equation? Q times of electric field E plus velocity of the charged particle into the magnetic field B. So, this equation we will call as a Lorentz force equation. This Lorentz force equation we will get for the magnetic field for the moving charged particle. The whole thing is represented with the figure. In this figure, in the magnet, two poles is there. First pole is north pole, another one is south pole. In between the forces exist. The force is maximum when magnetic field as well as velocity both are with perpendicular to each other. Both are perpendicular to each other means we are taking theta equal to 90 degrees and we are getting F equal to QVB. Next we will see magnetic force and a current carrying conductor. Suppose I am taking a current carrying conductor. The length of the conductor I am taking as L, from the fixed point some distance I am taking as a D, and the particles charge. Suppose in this conductor many charged particles is there, I am concentrating on a single charged particle. To this single charged particle, the fixed point distance is D, whole length is L, charge is Q, and current is taking as a capital I, and magnetic field B, and velocity is V. And with all these terms we have force. The force is represented with F. By taking all these, now we will see what we will get with the force. Previously just now we discussed what is force formula. Force equal to Q times of, there we discussed QVB. In this topic I am calling as a QVDB. What is VD here? Drift velocity. We will see magnetic force on a current carrying conductor. Consider a conductor. In this conductor we have current I, velocity V, magnetic field B, L is the length of the conductor, D is the some fixed distance for the single particle. Using this we already saw the formula. What is the formula we saw? F equal to QVB sin theta. In this theta equal to 90 degrees means we will get F equal to QVB. Here I am concentrating on the term current density J. What is current density? How much current is passed for the some area, cross sectional area, that is represented with J. Using this I am writing J formula here, drift velocity formula I am taking. Here drift velocity formula Vd equal to current density J times of J by NQ. N is the number of particles, Q is the charge. So, this number of particles for the unit volume I am calculating new force value. The new force value F equal to what we got? QVB. Actual formula of F equal to QVB. In place of V I am substituting J by NQ. Numerator and denominator QQ is cancelled and we are getting net force F bar equal to JB by N. This F bar equal to JB by N I am substituting in total force formula. What is the total force formula? N times of current I, A is the area of cross section by F dash. This F dash we calculated previous one, that one I am substituting the new force, and after substituting in the new force what is F? F equal to N times of current I, area of cross section A, and previous we calculated f dash. That previous calculated f dash equal to JB by N. This one I am substituting. After substituting JB by N, we will get f value. Again f equal to current N times of N current I, A is the area of cross section, whole I am getting. In this equation, just observe we have the term JA. What is that JA? That JA is I am concentrating as current I, and L is the length. After simplifying, I am getting the formula dF equal to I times of dL into B, where L is the length, B is the magnetic field. Suppose I want to represent this one in the vector form. Suppose I want to represent in the vector form, what we will write? Force formula. Force equal to current times of length into B. Here length and magnetic field both are in vector form. For that we represented with multiplication symbol. Suppose if it is a scalar form, we have to put dot, but this current as well as magnetic field and length, three terms are in vector form. So, I am representing F equal to current I times of length times of the magnetic field. So, what is this formula? This formula is for the force for the current carrying conductor consisting of moving charges. Now, next we will see the torque and a current loop. Suppose I am taking the current loop. That current loop is parallel to the magnetic field. In the figure, just see ABCD is a loop, current loop. That loop is in parallel to the magnetic field. Here we are representing with magnetic field B. So, after applying this magnetic loop to the magnetic field, some force is existing, but that force is in rotational direction after applying into the magnetic field. After applying to the magnetic field, just observe the figure, force F is in upward direction with B along. If you are taking theta, x axis we will take as B cos theta, in the y axis we will take as B sin theta. So, finally, what is the meaning of torque here? What is the torque definition? Torque is the product of force and how much distance we are applied. So, torque is the product of force into the distance applied. Its units, force units is newtons, distance meters units is meter. So, total torque units is Newton meter. Now, we will see this torque. So, what we discussed, magnetic field B, I am taking a loop. This loop and magnetic field both are in parallel with each other, then torque is produced. Torque is equals to force into how much distance it is covered, force into distance, Newton meter. Using this, again we will see the derivation for what is the formula for the torque. For that, already we calculated force formula. What is the force formula? I into L into B. Same formula I am using, and further derivation I will do. Here force I am taking as a current I times of the length into B, and I am taking this force for the small angle theta for small cross sectional area. Force into distance, that force I am taking as a F equal to Ft cos theta. After taking F equal to Ft cos theta, here I am substituting force formula. What is force formula? F equal to IBL, F equal to IBL cos theta. F in place of F I substituted IBL. I is current, B is magnetic field, L is the length and cos theta. Just from the equation, I took length part separately, and to that length I am differentiating using 0 to 1, cos theta integral 0 to 1 dl. That length I will get integration of dl, I will get L. So, the final equation for the force equal to IBL cos theta. Now, total torque I am calculating. The total torque formula equal to T equal to 2 times of force into distance by 2. Here what is the force formula we got? IBL cos theta we got. Just substituting IBL cos theta in that, I am getting final formula for the torque. Final formula for the torque equal to IAB cos theta. How we got A in the equation? In the previous equation we do not have A. In the previous equation we have IBLD cos theta. Here I am using IAB cos theta, because in the previous formula I times of distance D is treating as a area of cross section. In IBLD cos theta, I times of the distance I am choosing as a and substituting, then I am getting torque tau equal to IAB cos theta. So, this is the formula of torque. Using this torque, the torque is directly proportional to the current, and the torque is directly proportional to the magnetic field, and the torque is producing with some angle theta. So, the total formula of torque is equal to current I times of the area of cross section A times of the magnetic field B times of the cos theta. We will take torque formula. So, here to this torque formula I am applying some magnetic dipole momentum. In what we have formula IAB cos theta. What is our formula? IAB cos theta. In terms of IAB cos theta, there I am using some magnetic dipole momentum mu. IA and suppose I in times of A with number of turns I am treating as a magnetic dipole momentum. So, in the previous formula, wherever we have in the previous formula, just see the previous formula, what we have, tau equal to IAB cos theta. In place of I times of A, I am substituting magnetic dipole momentum mu. Then what we will get formula, torque tau equal to magnetic dipole momentum mu times of B times of cos theta, mu times of B times of cos theta. So, the overall formula of torque equal to magnetic dipole momentum into magnetic field B. Here also we are concentrating on a vector. So, we will write torque formula as a mu times of B. Next topic is potential energy associated with the current loop in a field. Suppose I said magnetic dipole momentum mu. B is the magnetic field. Suppose to this magnetic dipole momentum, I want to change its axis of rotation. What is the meaning of axis of rotation? Means to this magnetic field, I want to make it reverse, some rotation I want to make. When this rotation is possible? When some work is done on the particle, then some rotation will be takes place. So, here I want to change the direction of the magnetic dipole momentum. Some potential energy is applied to the particle. After applying the potential energy, now we will see how the derivation will be takes place. Here mu is represented with the potential energy, and the previous torque formula whatever we have, the extension we will do for the potential energy for the current loop. The potential energy for the current loop, previous formulas we will take. What is previous formula for the magnetic dipole momentum? Magnetic dipole momentum equal mu equal to number of turns into current I times of area of cross section, and also we have another formula for the torque. What is another formula for the torque? Tau equal to mu times of B sin alpha. Using these two things, I am deriving potential energy formula. Here what is potential energy? Mu B to this sin alpha, I am making integrating from 0 to alpha. Integral of 0 to alpha sin alpha, what we will get? Minus cos alpha we will get. Integration of sin is minus cos. So, we will get potential energy mu equal to mu times of B cos alpha, where mu equal to, suppose I want to write in terms of vector form. If I am writing in vector form, how we will write? Potential energy mu equal to mu naught times of magnetic field B, or else we can take mu equal to minus mu naught B. In the second equation we are not having minus symbol, but in the third equation we have minus symbol. Why it is? In the second equation minus is missed, but in the third equation we have minus, because while we are writing in the vector form, no need to take minus symbol. If we are writing directly formula, we have to include minus symbol. So, total potential energy mu equal to minus times of mu naught times of B. Here where mu naught is the magnetic dipole momentum and B is the magnetic field. Next we will see the formula. So, what are the formulas we discussed? We discussed two formulas. One is force. Force equal to ILB cos theta. Another formula we will discuss the torque. What is the torque formula we discussed? Mu B cos theta. Based on these two things we will solve a problem. Here what is the question? Take a rectangular wire. Suppose rectangular means we have length and breadth. Here length and breadth is 10 centimeters as well as 5 centimeters. In this I am taking some current. Current equal to 0.10 amperes, means the data is given in the question. We will substitute all these data in the question and we will calculate force. First we will calculate force. After calculating the force, we will calculate the torque. What is force formula? N times of current I times of magnetic field B times of length L. In the given question, he is given for 20 turns. So, I am substituting N as 20. And current is given as 0.10, that data is also substituted, and magnetic field induction B is given. Magnetic field induction is given as 0.50 Weber per meter square. After substituting the given data, we got force F equal to 0.1 Newton. After that torque is calculated. So, torque equal to force times of what we have to take, force times of magnetic field with some cos angle. Here what is the angle is given? The angle is given for 300 rotations. The direction is taking place for 300 rotation. So, after substituting the data, the torque is calculated. Here we got torque equal to 4.3 into 10 to the power minus 3 Newton meter. Why it is Newton meter? Torque equal to force into distance. Force is in terms of Newton, distance is in terms of meter. So, we are taking torque as a Newton per meter. Now, we will see the applications of the magnetic field as well as a magnetic force, where these are useful. These are used in AC as well as DC motors, transformers. Using these transformers, we can find the rectifiers, AC rectifier, bridge rectifier, full wave rectifier, off wave rectifier. Also, we are using resonance circuits, magnetic resonance imaging. Also, we are using the mass spectrometer in electromagnet. All electromagnetic topics is related with electromagnetic field as well as magnetic force. So, we can apply this magnetic force as well as magnetic devices to all magnetic topics or to all the magnetic equipment circuits. In this unit, we discussed magnetic field, magnetic force, torque, magnetic dipole moment. We will see one by one. Magnetic field, when the field is produced, when suppose a charged particle is bringing to the space, some field is produced. According to the field, some force is also produced. So, this field is only for magnetic particle of moving charges. Next, as well as same way we will produce electric field is also producing. This magnetic field is represented with B, electric field is produced with E. Using these two, I am calculating Lorentz force equation. The Lorentz force equation F equal to charge Q times of electric field E plus V times of B. This is the Lorentz force. Again, what happening to the magnetic force when we are keeping in the charged particle? Suppose field B as well as velocity V, both are perpendicular to each other. What happens to the force? Force is maximum, which is 90 degrees. Suppose it is the charged particles are in parallel or anti-parallel. At that time, force equal to 0. V and B are not perpendicular to each other. So, force we have two cases, either force equal to 90 degrees or force equal to 0 degrees. So, this force equal to 90 degrees and 0 degrees we are using for the moving charged particle. Next, after discussing the moving charged particle, we will come to the how current is flowing in the conductor. The current is flowing to the conductor, we will take the equation F equal to ILB sin theta. ILB sin theta, here I is the current, L is the length and B is the magnetic field. This after derivation of this one, here we will come to the torque. If what is torque? Force into distance, force is F, distance is M, Newton meter we will take. In this torque, I am taking a loop, this loop is parallel to the magnetic field. Suppose loop is parallel to the magnetic field, how the loop is rotating after magnetic field is affected? From there, force formula is substituted and we got final equation. From there, I am taking magnetic dipole momentum mu, magnetic dipole momentum substitution. Final, we will get torque formula is equal to mu B sin theta. If theta equal to 90 degrees, we will get mu B. If theta equal to 0 degrees, then torque equal to 0. Next, we will see how potential energy is produced. Suppose a particle experiencing some torque. I want to make the direction of rotation, I want to make some rotation of direction. If rotation of direction is not easily possible, we have to apply some work done. After applying work done, what is total potential energy we are calculating? Using total potential energy, we are simplifying that what is the value of U that is derived from the magnetic dipole momentum. So, final conclusion, we discussed magnetic field as well as magnetic force and magnetic dipole momentum, and this how moving charges is affecting when it is passed through the current carrying conductor.